hydrocarbons, as substances containing hydrogen and carbon, burn, and they create carbon dioxide, which is what people regularly know. However, most people don't know that when you burn hydrocarbons, another product is water. You simply can't see the water because it's in a gas form when it's released and goes elsewhere into the atmosphere. But in this experiment, we're going to take the container and we're going to cool it, and there's going to be water droplets on the inside of the container due to the water produced from the burning. Everything in this equation is gas. So we're going to pour liquid alcohol and wait for it to become a gas, and then we're going to ignite it. Loosely capping it, the alcohol can evaporate, but not escape into the air around us and stay trapped in this medium-sized jar. Spinning the jar to increase the surface area of the liquid alcohol to make sure that it evaporates faster. At this point, you can see that there is no liquid alcohol left in the jar, and it is all evaporated into a gas inside of the jar. At this point, I'm going to light the gas, and it's going to burn the oxygen in the gas. In the container. Here we go. It's not going to do anything. Yep. You now see that the water is beginning to condense on the sides of the container, forming small water droplets. You can now see the water that is condensed inside of the jar. So, why does ice float? The answer to that question is, ice is less dense than water. Therefore, it floats on top of the water, which is heavier than itself. If it was put on some liquid that is less dense than it, it would supposedly sink. But we're just going to use water. Ice cubes wrong. Now, I know what you're thinking. You're probably thinking, that's not ice. This is indeed ice. It's liquid. It's wrong. This is ethanol. It's not water. This is water. Ice does float in water. Now, ethanol is much less dense than ice, and that's probably the reason why the ice sank. Little bonus video, why waste perfectly good ethanol when you can burn it? Extinguish this. Electricity is the flow of charge. Water does not conduct electricity because there's nothing for the charge to flow through. It's neutral. The hole will light up if anything conducts electricity in the solution. Ethanol is also neutral, and ethanol doesn't conduct any electricity, and nothing will happen. Sugar is also non-conductive, and even when dissolved, will not do anything. Sugar is also a neutral molecule, and will not conduct any charge, electricity to throw. Salt does conduct electricity, and there is basically a charge to flow through. And as you can see, the electricity is blowing, and the light bulb is lighting up. Today, we have all these metal salts, and we're going to be creating different color flames. The reason that the flames are different colors when you add different metals is because of the electrons. The electrons in the atoms of the different metals that you're going to use to create colored flames are going to absorb a lot of energy from the fire that we're going to make from the gas. And then when they're coming back down, they're going to emit colored light, such as purple and red. Most of these metals may look the same except for copper, but they're actually completely different metals and make totally different colors. The first metal is lithium, which is going to make a red color. It's very red, as you can see. The second metal is strontium, this one. Closest strand. It's kind of orange. Next metal we're going to burn is calcium. It's also orange. Next is sodium, or yellow. Next is boron. Greenish, I think. Next is copper, which, as you can probably guess, will make green. Cool, huh? Last but not least is potassium, which will burn purple. It's very faint, and also the flame is kind of purple, so you can't really see it. But if I do it up higher, you can see that it is indeed purple. Now we're doing different colors. Bonanza of color. Boom, color magic. Yay for colored fire. We're doing a vanadium lab. Oxidation is losing electrons, and reduction means gaining electrons. In this lab, I'm using the zinc, the vanadium. The zinc is going to be losing electrons to the vanadium, which will be gaining electrons, and each time it gains an electron, it will absorb a different color of light and change colors. First, I'm just pouring a bit of vanadium into this one. Remember what it looks like. I'm pouring it into the zinc. So let's start. As you can see, it's already turning green. So pour some of that green color into this one. Without losing any of the zinc. Swirl it some more blue. You can see it's now kind of blue. blacker color. I think it's gonna turn purple. I think that's close as purple as we're gonna get. Just pour that. We have our different colors of Canadian. Today we're going to be performing electrolysis as we did in class. This is a salt-based solution, so it should conduct electricity, or it will. It's a universal indicator. We're going to be using it in electrolysis to split water molecules, making hydrogen and oxygen. The oxygen is going to be red, and the hydrogen is going to be purple. The reason for this is when we're making the hydrogen, we'll also be making a base, which will make the indicator turn purple. And on the oxygen side, we're going to be making an acid, making it red. Starting electrolysis. Knock this over, I'm clumsy. As you can see, there's more purple than red. The reason for this is because there's twice as much hydrogen in the water molecule as there is oxygen, because there's one oxygen and two hydrogen. So it's stirring it up more because there's twice as many bubbles of hydrogen. So that's why there's more purple. But we are making the same amount of acid and base, so when we mix it together, it will go back to green.
Say something stupid.
Something stupid.